Hello everyone, my name is Kaiqing Liao. I'm a postgraduate student in the School of Computer Science and Engineering, Central South University. I'm honored to participate in the SCPP 2020, and I am glad to share our research with you. The topic of our research is periodical strategy for the 40 to 100 gigabit per second energy efficient Ethernet. Next, I will introduce our research content from the following 5 parts in sequence. First, I will introduce the introduction. Nowadays, the 40 to 100 gigabit per second Ethernet appears in commercial usage. This huge energy consumption issue has attracted the researchers' attention. In 2014, 40 to 100 gigabit per second energy efficient Ethernet standard was promulgated, which provides to low power states to reduce power consumption. The strategy design is crucial for power saving and latency. The longer the time in low power states, the more energy saved, and the greater the transmission latency of the data frame. Besides, the EE applications place a constraint on tail latency. Our contributions are as follows. We designed a periodical strategy, for short PS. PS can first satisfy the given latency constraint by limiting the largest incurred latency at the length of the cycle, and maximize the power saving in each cycle by selecting the low power state based on the prediction of incoming frames, as well as dynamically reserving time for frame coalescing. What's more, the periodical behaviors make PAs insensitive to different traffic patterns. Then I will introduce the background and related work briefly. In Figure 1, the 40 to 100 gigabit per second EEE has 3 states. The two low power states power consumption ratio is 70% and 10% of that in the active state, and the frames can only be transmitted when the interface is in active state. Notice that the transition time related to fast wake state is much shorter than the deep sleep state, except for the time spent in low power states. The corresponding transition processes also affect the energy saving and the delay performance of the strategy. There are several good energy saving strategies. Dual model is a greedy energy saving strategy. In dual model, the EEE interface always enters fast wake state first, and then sets up a fixed timer TF. After the timer expired, the EEE interface will turn to deep sleep state when no frame arrivals. Otherwise, the interface will be waked up from the fast wake state. In sum, dual model could only yield limited energy saving. FC has two fixed thresholds in its design. In FC, the EEE interface enters the fast wake state first and transforms from fast wake to active state when the number of frames arrived within TF is larger than threshold CF, or the interface will enter into the deep sleep state when the timer expires and the accumulated frames are less than CF. Later, the interface will be waked up from deep sleep state after the number of coalesced frames exceeds the threshold CD. In FC, the timer to exit low power state mainly depends on those fixed counters. Thus, FC would significantly increase the latency of frames, especially in the light load. Tail latency can be unacceptable. The FC-SSHI strategy utilizes LPI_FW flag to select a low power state. When the previous accumulated frames are larger than half of the CD, the flag will be set to true. The EE will enter into fast wake state for next transition. Otherwise, the EE will enter into deep sleep state. After the timer expires or accumulated frames exceed the CD, EEE will leave the deep sleep state. Compared to FC, the timers set for those low power states are used as a complement of counters, which alleviates the problems that exist in FC. Besides, FC SSHI provides an option of low power state. However, the option depends on a fixed parameter set by experience. The FCDT strategy sets its counters according to the equation 1. If the expected average latency WS is smaller than given target latency W, which is associated with link capacity, the FCDT will select fast-wake state for state transition and estimate the counter CF for frame collision. Otherwise, FCDT selects deep sleep state and estimates a counter for frame collision. Before the WS changes, FCDT only uses one low power state. In sum, FCDT dynamically sets the counters to control the time that the EE interface stays in a low power state, but it will only utilize one low power state once the expected average latency is chosen. From the above descriptions, we consider there is room for improvement in FCDT and FCSSHI in terms of facing different traffic patterns. In Figure 6 and Figure 7, FCDT and FCSSHI do not spend time in low power state and suffer from high power consumption. In this table, we summarize the advantages and the disadvantages of the above strategies. Next, I will introduce the PS in detail. We first introduce the basic framework of PS. The figure shows the state transition of PS. The starting and ending point of each cycle is both the time when the buffer becomes empty, and the link is going to transform from an active state to a low power state. At the end of each cycle, PS predicts the time tau reserved for the transmission of the predicted number of frames. What's more, PS computes the time etc subtract tau for the frame collision and select a suitable low power state based on the time. Next, the EE interface transforms into the selected low power state directly and wakes up for data transmission when the rest of time in this cycle equals to tau. We think that PS outperforms other strategies in energy saving because PS dynamically chooses the low power state and adjusts the frame collision time. PS relies on the configuration of its expected timeless of cycle etc to fulfill the latency constraint given by EE applications. To suggest the setting of etc, we conduct an analytical model for the latency distribution of frames in each cycle of PS. From the analysis, T99 is probably bounded by the etc. That is to say, PS limits the 99th tail latency by configuring the etc according to the given latency constraint. This mechanism helps to decouple the power saving and the tail latency constraint. After considering the etc, we will predict the number of frames that arrived in the current etc. At the end of each cycle, we use the EWMA method or ARMA model to predict the number of frames within the previous cycle's information. Then we compute the time etc subtract tau for frame coalescing. Then by combining periodical behaviors with predictor methods, we could dynamically adjust the time for power saving according to different traffic. After we obtained the time for frame coalescing, we calculated the corresponding power consumption for each low power state and then select the better one. The selection results of the low power state are shown in the above table. The dynamic state selection makes PS save power as much energy as possible on the different traffic patterns. What's more, because the selection of low power states depends on boundaries shown in Table 1 rather than the concrete number of incoming frames in each cycle, small prediction error would not violate the selection result. While the FCSSHI and FCDT select low power states according to a fixed value. The prediction error has little impact on PS. On the one hand, even though prediction error has an impact on the real timeless of cycles, the incurred latencies of frames are bounded by ETC, so the given latency constraint can still be satisfied. On the other hand, because state selection is based on boundaries shown in Table 1 rather than a concrete number, small prediction error would not violate the selection result. In addition, the impacts of prediction error on power saving is limited. In brief, this is because PS periodically gathers the chance of energy saving together in every cycle. As shown in the figure, prediction errors of consecutive cycles can cancel each other out. When the accumulated prediction errors are large enough, PS would keep staying at the active state or deep sleep state for whole ETC to balance the accumulated error out. Compared to considered strategies, PS is insensitive to traffic load variation. Then we will evaluate the PS strategy. We implement PS by extending the Ethernet channel object of NS3. The default configurations are the same as considered strategies. We evaluate the performance of PS on the several traffic generators. We first analyze the properties of PS. As shown in Figure 9, the latency increases and the power consumption decreases with the increase of ETC. At the same time, the 99th tail latency is always below ETC. We find that the given latency constraint can always be satisfied, and we conducted the rest simulations with ETC equals 10 microsecond and 40 microsecond. Next, we evaluate the PS, FCDT, FCSSHI under the specific traffic scenarios as depicted in Figure 6 and Figure 7. As shown in Figure 10 and Figure 11, the performances of both FCDT and FCSSHI are extremely poor under certain traffic pattern, while PS still has lower power consumption. Meanwhile, although the 99th percentile latency of the PS is larger than that of FCDT and FCSSHI, it is still restricted by the parameter ETC equals 40 microsecond, which means the given latency constraint is satisfied. Subsequently, we compare different energy-saving strategies in detail, as shown in those figures. PS has lower consumption under the different given latency constraint. Next, we compare different energy-saving strategies under self-similar traffic. Under the condition that the given latency constraints are satisfied, PS achieve the best power saving. Finally, we use the real chases to evaluate the performance of FC. When the given latency is 40 microseconds, all strategies satisfy the requirement. PS has the lowest power consumption, and when the given latency constraint is 10 microseconds, dual model FC, SSHI, and PS satisfy this requirement. Their power consumption ratio are 0.94, 0.83, and 0.82. In sum, PS outperforms all other considered strategies in terms of power saving under the given latency constraint. In general, we designed the periodical strategy for 40 to 100 gigabit per second EEE. The PS decouples the power saving and the incurred latency of frames, and the PS is insensitive to traffic patterns because of its periodical behaviors. Moreover, PS achieves a good energy saving under the given latency constraint. Thank you.